Hi, it's me, Tim Dodd, the Everyday Astronaut. Behind me is SpaceX's Starship prototype, and it's missing something. Well, actually, it's missing a lot of stuff right now, but one thing that's missing that there's no plans to put on it is a launch escape system or a launch abort tower of any kind. No mechanical aborts are going to be on this rocket at all. Is that a good idea? Hindsight's always 20/20, and one of the biggest criticisms of the Space Shuttle, which also claimed to be reusable and airliner-like reliable, was that it didn't have any kind of launch abort system. And that's the same type of thing SpaceX is claiming with the Starship. So are we doomed to see history repeat itself? And as we know, SpaceX's Dragon capsule and Boeing's Starliner both have had problems with their launch escape systems. So today we're going to debate, is all that extra stuff necessary? Does it actually make for a safer vehicle? And hopefully by the end of this video, we'll know whether or not it's a good idea to put people on top of this rocket without any kind of mechanical abort system. Let's get started.
3, 2, 1, liftoff. That's one small step for man. Contact with a test 1.
This is another one of those topics I've been asked about over and over, and for a good reason, especially now that we're seeing the commercial crew program put launch abort systems through their paces. And this has become even more relevant ever since we witnessed the failure of the Mark I Starship prototype down in Boca Chica while it was pressure testing on the launch pad. I mean, what if there were people on board? Why isn't SpaceX thinking about putting a launch abort system on it? Now, as you may know, I've already talked a good amount about launch abort systems in a video explaining why both SpaceX's Crew Dragon capsule and Boeing's Starliner have opted for liquid fuel pusher abort systems, as opposed to a more traditional puller system with solid rocket motors. So if you need an overview on those systems, definitely check that video out. It should help give you some extra perspective on modern abort systems. Now, in case you didn't notice when you clicked on this video, this is again another pretty long one, because as you may know, I don't really like to just skim the surface of topics. I like to actually dive in deep and get into the data and the history in order to find the answers. So we're going to get into a lot of little details, charts and data, and more charts and more data. We'll go over the certifications of rockets, the reliability of rocket engines, the risks and benefits of Starship's designs, and even look at the whole history of human spaceflight and figure out how many times an abort system has actually saved the lives of those on board. By the end of this video, it won't just be my opinion on whether Starship without an abort system is a good idea or not. It'll mostly be an analytical-based summary. So to make this all easier for your viewing pleasure, here are the timestamps of each topic we're going to talk about in case you want to go back and review something. There's also links in the description below to those timestamps and an article version of this video as well for you to easily go back over some of those numbers and sources. Okay, so abort systems. The idea is pretty simple. Rockets are fickle beasts. I mean, they're riding the finest engineering line possible. They need to handle extremely intense loads, temperatures, and environments while also needing to be as lightweight as possible. And since there's literally millions of moving parts, it's honestly a miracle they even work at all. So when you're putting someone on top of a vehicle that's basically just a giant bomb with a nozzle that has to have millions of parts work properly in order to not fail, it's generally considered a good idea to have a backup if things don't go as planned. Throughout most history of human spaceflight, there's been one method that has dominated launch abort systems, and that's a solid rocket motor launch escape tower. This is that tower that sits on top of the crew module that you may have noticed on vehicles like Mercury, Soyuz, Apollo, and even NASA's Orion capsule. A few vehicles like Vostok, Gemini, and early space shuttles had ejection seats as an escape system, and I've already got a video all about that if you want to hear more about it. But regardless of whether it's an ejection seat, a launch tower, or a more modern liquid pusher system, the concept's the same. If the escape system detects either a loss of thrust, a severe deviation in flight path, or even detects a rupture in the tanks, it'll trigger the abort system. Early rockets, and probably some modern ones, I couldn't actually find the answer to that, have an actual trio of sensor wires running the length of the fuselage. Now, if any two of those wires lose contact, this indicates that the fuselage had broken up, which then would trigger the abort system. The launch abort system can also be manually triggered by an astronaut who may, notice some kind of critical flaw that the system doesn't detect. Once an abort system is triggered, the stage separation system needs to let go of the spacecraft as the abort motors are fired, so it can pull clean from the rocket. When the motors actually fire, it accelerates the crew capsule away extremely quickly. I mean, abort motors can pull some serious Gs, like over 10 Gs. So launch abort systems were pretty much considered the best way to keep a crew safe. But what if you just made your entire system more safe? What if you had a more redundant system and over-engineered every single part to even greater safety margins? Designing a rocket to be as reliable as an airliner? That's exactly what NASA was hoping to do when engineering the Space Shuttle.
The vehicle is called the Space Shuttle, an airliner-like spacecraft capable of over 100 trips from Earth into Earth orbit.
The thought being, if every single part of the Space Shuttle was over-engineered, the chance of loss of vehicle and crew would be very low. So low, it might actually be safer than adding additional moving parts and additional systems necessary to make an effective launch abort system. During the Apollo era, when NASA had what now seems like unlimited funding, they contracted General Electric to do a full numerical probabilistic, how do you say that word? Probabilistic, sure, risk assessment of landing a human on the moon and returning them safely to Earth. The number GE came up with was 5%. A 5% chance of successfully landing a human on the moon and bringing them home. And now NASA Administrator James Webb didn't really like those numbers. And so instead of making changes to the rocket and the mission, they decided to change the way they engineered around risk, which, let me point out, isn't necessarily a bad thing. They developed something called the failure modes and effects analysis, which was a way to identify designs and hardware that would, worst case scenario, lead to catastrophe. These are ranked as criticality 1, which would threaten the life of the crew or the existence of the vehicle, criticality 2, which would threaten the mission, or criticality 3 for anything else. They also added an R as a notation for redundant systems in these parts and design analyses. With NASA's budget beginning to dwindle once humans landed on the moon and congressional support for the upcoming shuttle program waning, NASA had to sell the space shuttle as a cheap and reliable workhorse. And its exact risk even had to be calculated in order to launch plutonium-fueled spacecraft like the Jupiter probe Galileo. Testing the reliability of a complex system involves studying the system as a whole, identifying potential fault points, and then gathering the limits of these potential fault points over different environmental conditions. You also then test them in statistical models and computer simulations these days, and iterating on them to make sure that the computer simulations meet the real-world performance in order to help determine if the probability of success is above the threshold required. Each and every single part will have a design specification and a certain safety factor for how much more it can handle beyond its design specification. The general rule of thumb for most parts on a rocket is a factor of safety of 1.5. And all this really means is if a part needs to handle 10 newtons of force when testing it, it should be able to handle 15 newtons of force without failing. But when there isn't good test or heritage data for a certain part, a factor of safety of 2.0 is considered a good rule of thumb. In other words, engineer it to handle twice that of what's necessary. By the start of the Space Shuttle program, estimates of catastrophic failures ranged from less than 1% to less than 0.001%. So actually a couple of orders of magnitude in its estimated range of predicted safety. Now, despite the optimistic nature of NASA, the first 4 flights of the Space Shuttle had ejection seats active, but were later ditched due to their very limited use cases, and the fact that they could only eject crew from the upper deck, since the rest of the crew was on the mid-deck, which was below them. But after the Challenger disaster, NASA did actually consider utilizing an ejection cabin that could eject the entire crew module free from the shuttle, kind of like F-111s and early B-1 prototypes. But it was deemed too complex, too heavy, and required way too many modifications to really make it feasible. Okay, so in hindsight, we know the shuttle wound up with 2 failures out of 135 flights. One during launch and one during reentry, giving it a success rate of only 98.5%, which is way off from even the most conservative estimates of safety. Likely due to the Space Shuttle's track record, NASA changed their certification system for the commercial crew program, which is required to have a probability of loss of crew at 1 in 500 on ascent, 1 in 500 on descent, with a 1 in 270 chance of an issue while in orbit. To actually certify and validate the system, sometimes it just comes down to putting it all through the ringer to test the system as a whole, alongside with testing each individual part. Now, testing the system as a whole is called all-up testing, or that's kind of what NASA coined it during the Apollo era. In the long run, all-up testing might actually be a quicker route to verify the system versus acquiring certification through more ground tests, analysis, and using heritage data that might require a higher factor of safety per part if it's not going to be tested as a whole. You can see this difference in methods play out today and how SpaceX chose to validate and certify their abort system by opting to test it in flight, while Boeing has opted to certify their abort system through a more stringent certification of individual parts. Since the Space Shuttle and Starship both lack abort systems, what design considerations did the Space Shuttle have that were so dangerous? And does Starship share any of those same flaws? There's a few things that made the Space Shuttle inherently kinda dangerous, but let's start off with those solid rocket boosters. Those giant white solid rocket boosters on the side of the external fuel tank actually provided over 60% of thrust at liftoff. But here's the thing, once they ignited, there was no shutting them down. You're going somewhere, and you're going somewhere in a hurry. So hopefully the pointy end is up and the flamey end is down. This meant any abort mode or any abort procedure, no matter how bad or dire, required the crew ride out the boosters. Seriously. So for an entire 127 seconds, if there was any kind of problem, you just had to cross your fingers and toes that it wasn't going to be too serious and you could keep going. This is mostly because if you were to abort by, detaching the orbiter from the external fuel tank or by trying to jump out, you'd end up within the plume of those SRBs, which would be very, very lethal. Now, unfortunately, some of those problems you just can't ride out. Like on January 28th, 1986, when the Space Shuttle Challenger took to the sky on its 10th mission. As you probably know, a leaky O-ring that sealed one of the sections of the solid rocket boosters sprung a leak, which ended up causing a separation of the joint that held the SRB to the external fuel tank, which then led to a complete structural failure of the vehicle and the tragic loss of the crew of 7. But perhaps the biggest problem with the Challenger disaster wasn't a hardware problem, but a problem with the program management and pressure to get that particular flight off the ground. I mean, it was already known that they'd be launching outside of the predetermined operating envelope of those SRBs, and it was recommended to not launch that day. Now, if they had utilized liquid-fueled rocket boosters, they probably wouldn't be able to eliminate all potential failures, and it could arguably be less reliable than a solid rocket booster, but liquid rocket boosters can at least be shut down, which in general can open up more abort options. Take a look at this chart. Notice the black sections. Those are sections of ascent where there would be a full loss of control and or structural failure if the vehicle were to lose 2 or 3 main engines. So basically, lose 2 out of the 3 main engines and you're screwed. And you're not even talking about having any problems with the SRBs or anything else. But after the Challenger disaster, NASA did come up with a lot more contingencies, including alternate runways and the iconic orange advanced crew escape suits to, escape. If things went wrong, literally escape. Okay, yeah, here's the new abort profiles, and see these gray sections during ascent? Now the plan was for the crew to literally jump out during those sections, as in carefully ditch the external fuel tank, get the orbiter into a stable glide, literally unbuckle, blow the hatch, extend a freaking pole that made it so you wouldn't hit the wing when you jump out, and then jump out. Seriously. Speaking of hitting the wing, that's another major flaw of the Space Shuttle. The orbiter was hanging off the side of the vehicle, which put the crew module and the fragile thermal protection system directly in the path of ice and foam strikes. That orange external fuel tank housed cryogenic hydrogen and oxygen, which had a good amount of insulation in order to keep them at operating temperatures. You can actually see sheets of ice fall off basically any liquid-fueled rocket at liftoff. It's a known variable, and even large chunks of foam were observed falling off the Space Shuttle's external fuel tank, but NASA grew more and more accepting of this fact. When you combine a large chunk of foam and the fragile nature of the thermal protection system on the Space Shuttle, you wind up with a real potential for disaster. And this is exactly what caused the Columbia failure. A large chunk of foam struck the leading edge of Columbia's wing on ascent, punching a large hole in the reinforced carbon-carbon section of the thermal protection system on the left wing. The shuttle and the 7 crew on board continued to carry out their mission for 15 days with a hole that would doom them on re-entry. On February 1st, 2003, as Columbia re-entered the Earth's atmosphere, the large hole in the wing caused hot plasma to essentially destroy the wing, and therefore the orbiter, tragically ending the 7 crew's lives who were on board. Now, besides the orbiter being slung off the side of the rocket and in harm's way of falling debris, the danger was amplified by how fragile the Space Shuttle's thermal protection system was. The Space Shuttle's 24,000 plus silica tiles were literally glued onto the aluminum airframe of the orbiter, which covered the entire bottom portion of the vehicle. Their fragile nature caused not only many headaches, but also led to some close calls. Perhaps the most well-noted was STS-27, which experienced a debris strike 85 seconds into the flight. This knocked a tile clean off and damaged over 700 other tiles. Whoa. In the absolute luckiest of circumstances, the tile that went missing was right on top of a steel mounting plate for the L-band antenna, which steel has a higher melting point than the aluminum airframe, and by sheer luck, the orbiter survived re-entry, and it didn't end up as a disaster like Columbia would some 15 years later. Okay, so now that we know some of the major design flaws that plague the Space Shuttle, let's go over Starship and see how its design differs. Well, right off the bat, Starship is on top of the super heavy booster and not slung off the side. Now, as we've noted, this is clearly a safer place for the crew cabin to be, putting it ahead of any potential debris strikes. But we should note something that will definitely need to be studied. Now remember, Starship has those large flaps that are vital to its re-entry. This does mean there'd be potential for ice from the liquid oxygen and liquid methane tanks on the Starship's upper stage to strike the leading edge of those flaps. But here's where a stainless steel body and the fact that the thermal protection plates will be bolted on has a huge advantage over fragile silica tiles and reinforced carbon-carbon covering an aluminum airframe. So let's not forget the leading edge and the underside of the flaps of Starship will actually utilize a heat shield, but unlike the silica tiles of the Space Shuttle, they're supposedly much more durable and actually bolted to the airframe instead of glued. And we've actually already seen SpaceX test heat shielding mounting and material options on Starhopper, putting them through extreme environments, vibrations, and temperatures. They've also experienced re-entry when SpaceX put a few small pieces of the Starship heat shield on a Dragon capsule to observe it through re-entry. Steel body panels and some variant of a tough rock heat shield bolted to the airframe should be more resilient than the Space Shuttle, considering steel can dent and ding and won't completely shatter like reinforced carbon-carbon or simply fall off like the silica tiles. But also, just like STS-27's lucky brush with death, steel has a much higher melting point than aluminum. This allows for a much greater tolerance to heat than the aluminum airframe of the shuttle, as we've talked about, but as a matter of fact, it's likely that Starship could actually almost survive completely intact with little to no additional heat shielding, as other stainless steel components have survived re-entry pretty much completely intact. Now, I've already done a video about that because they had even talked about having it bleed fuel to do a form of transpirational cooling, but that's since kind of either fallen off the table or might be utilized in some hot spots. Now, this is one of the biggest reasons why SpaceX switched to stainless steel over carbon fiber, because by the time you factor how big of a heat shield is necessary, stainless steel starts to come ahead, as it can handle much higher temperatures in general before it begins to fail. Okay, so hopefully a stainless steel body and a more resilient bolted-on thermal protection system, along with putting the Starship on top of the rocket stack, they should all help mitigate the risk of a re-entry disaster like Columbia. Okay, so now how about putting this on top of a rocket booster that will have at least 37 of the world's most advanced and complicated engines? And that is, of course, the full flow stage combustion cycle Raptor engine. I mean, how could this possibly be safer and have less failures than a simple pair of solid rocket boosters that have virtually no moving parts? Now here's where SpaceX has some good experience and knowledge. Their Falcon 9 does something fairly unusual in the rocket world, which is having 9 smaller engines on the booster instead of 1 or 2 larger ones. And this actually allows for multiple engine out capabilities. Now, depending on which engines fail and at what point in their flight they do fail, 9 engines gives the Falcon 9 a lot of extra safety margin compared to other rockets. Each engine is actually isolated within a blast containment cell as part of the OctaWeb configuration. This is why they can have an engine fail and have it not affect other engines. Now, you mix this in with modern sensors and quick-acting computers, and the rocket should actually be able to shut an engine down before that engine has a catastrophic failure. SpaceX has developed their Merlin engine to the point of extreme reliability. I mean, in fact, only one Merlin engine has ever shut down in flight out of over 800 Merlins being flown to date. Not to mention, that failure was very, very early on in the program, the 4th flight of a Falcon 9 for mission CRS-1, to be exact. And since then, the engine has been 100% reliable. So in total, the Merlin engine to date has proven to be 99.88% reliable. Now you mix that with the redundancy on the first stage, and you wind up with an incredibly reliable booster. Not to mention the fact that some of the Merlins on the first stage of the Falcon 9 have to fire up an extra 2 or 3 times per flight in order to land. Now, just for funsies, let's actually take a look at some other rocket engines throughout history and see how reliable they have been. But just a little caveat, it gets really difficult to just say reliability because there's so many other factors, especially when you factor in, relighting of engines or running out of T-tab ignition fluid or something like that. But still, looking at these numbers should give us a decent perspective on how reliable liquid fuel rocket engines can actually be. So again, SpaceX's Merlin engine is currently at 99.88% reliability in flight, which makes it slightly more reliable than the RS-25 Space Shuttle main engine, which also only shut down once in flight, but with only 3 engines on 135 missions, it wound up with a 99.75% reliability in flight. Then there's the RD-180, which technically shut down 4 seconds early on one of its 86 flights to date, making it 98.83% reliable. Although it's also kind of 100% reliable since that particular mission, OA6, was able to continue on and still be a success, but just barely. So we can say between 98.83 and 100% reliability, depending on how you define engine reliability. I mean, shutting down before intended is considered a failure of the engine. Had that happened at any point before that, the mission would have failed. But I would consider it a successful mission for the Atlas V, since the Centaur upper stage could compensate for the failure. But how about another Russian engine, the RD-107 and its brother, the RD-108, that power the Soyuz rocket? Now, this rocket has flown so many times and for so long in so many different forms, it's definitely not fair to compare the early days of the Soyuz rocket. Besides that, the data's really hard to find. So let's look at the 267 flights in the 21st century, which use an RD-107 and RD-108. And of the 1,335 engines fired in this century, only 1 has failed, giving the RD-107 and the RD-108 a 99.92% in-flight reliability. But one of the most reliable engines ever flown was actually the monster F1 engine that powered the Saturn V. The 13 times the Saturn V flew, all 65 F1 engines that powered those flights were 100% successful. Now, before you hop into the comment section and say, but didn't Apollo 13 have a center F1 fail? Nope, that was a J2 engine on the second stage. There seems to be this Mandela effect on F1 reliability, where everyone, including myself, tends to think an F1 failed on ascent. Okay, so let's assume there's going to be a ton of data on the Raptor engine since the Starship has so many of them, and since they can fly Starship a few times over and over, that SpaceX will eventually match the reliability of the Merlin engine. With multi-engine out capability, the booster should be a very reliable first stage. Now, assuming SpaceX does their due diligence to prevent an engine failure from affecting other engines nearby, like they have done with the Falcon 9, and like how the N1 didn't do a very good job of that, having dozens of engines can actually make for an incredibly robust and reliable vehicle. Okay, sure, having dozens of engines on ascent could help make the booster safe and reliable. But what about the big elephant in the room? In order for humans to survive a ride on Starship, the Starship itself has to not only perform a pretty wacky landing maneuver, but it also relies on 2 out of 3 Raptor engines working for the landing burn itself. Now, is that actually safe? Can we really rely on propulsive landings for human lives? Well, let's go ahead and take a look at the Falcon 9 again, as it's one of only 2 vehicles in history to perform propulsive landings after reaching space. But remember, it isn't reaching orbital velocity either, like Starship is, so we're only really going to be looking at the landing aspect of it, just the landing burns and using engines as propulsive landings for now, because the very end of Starship's propulsive landing burn will look and actually function almost exactly like the Falcon 9's. To date, SpaceX has landed 46 out of 54 landing attempts. Now, that doesn't sound great, but remember, before the first landing, it was literally considered impossible. Like, no way. When it happened, it was a really big deal. Now, if we look at just the landing attempts starting in 2017, after it became a little less experimental and they kind of had it figured out, we get some pretty surprising numbers. There's been 45 attempts since 2017, and only 3 of those were failed landings. None of those 3 landing failures was due to a failure of a Merlin engine itself, although again, that kind of gets complicated. Going in order, on February 6, 2018, SpaceX launched the first Falcon Heavy on its demo mission and landed all but the center core of the Falcon Heavy. The center core ran out of TTAB, which is that pyrophoric starting fluid that actually ignites the engines. It sounds like there was a pretty easy fix, and it wasn't actually that they would need more TTAB, but just needed to switch which bottle it pulled the TTAB from and at what point to solve the problem. Then later that year, on December 5th, 2018, for the CRS-16 mission, a brand new Block 5 Falcon 9 core failed to land when the hydraulic system that controls the grid fins seized up. The solution was simply a bleed valve that would prevent it from happening again. Now, as far as the Merlin engine goes in that, it performed perfectly fine and allowed the vehicle to touch down so soft that it didn't really even break apart and could actually just be towed back into port. Lastly, the latest Falcon Heavy launch on June 25th, 2019 for the STP-2 mission had a failed center core landing attempt as well. SpaceX didn't actually expect the core to survive re-entry due to extremely high velocities and pushing the vehicle to the absolute limits. As far as we know, the actual engines themselves still lit up and performed fine, but the thrust vector control that steers them was actually destroyed due to that spicy re-entry heat, which made the vehicle lack precise control for landing. So the engines themselves were fine, but, you know, TVC kind of got destroyed, so it's kind of hard to say. Since this was at the outer limits of what that booster was capable of doing, the solution is simple. Just don't push it that hard if you need to land. So if this were a Starship mission with people on board, they would have made sure there were healthy enough margins that are safely within the operational range of Starship and not even accept a mission or design a mission where they push it to the limits in the first place. So can we ever rely on propulsive landings for humans? I mean, eventually, sure. I mean, think about it. The Apollo missions relied on propulsively landing on the moon, and that worked out pretty well. But as far as everyday usage, as long as there's redundancies in place, having 3 engines light and having engine out capability is a good place to start. But what about all the other systems in place on Starship? I mean, what about those giant wingy, flappy fin things? What if the hydraulic system fails on those and they get stuck? You know, like what happened on CRS-16. Well, for this, we need to look no further than airliners and the space shuttle. Here's where good old redundancy comes into play. Airliners would lose control and be unable to operate their gear as intended if the hydraulic system failed. I mean, same thing goes for the space shuttle, which is exactly why there are redundant generators, redundant pumps, redundant lines. Basically, everything in that system is redundant. And it's actually not very wise to compare the CRS-16 failed hydraulic system and say, see, what if that happens on Starship? Because a Falcon 9 booster landing isn't mission critical, let alone required for human safety. So they have intentionally lacked redundancy for simplicity. But there's one big thing that isn't redundant and can be catastrophic if it fails. And boy, do I mean big, because that's the fuel tank / the fuselage. And this is honestly my biggest area of concern, and to be quite frank, it's the one thing SpaceX has had bad luck with over and over and over. The first failure of a Falcon 9 was due to a helium-filled composite overwrap pressure vessel, or COPV. These pressurized the fuel tanks and oxygen tanks, and one broke loose in the upper stage oxygen tank on June 28, 2015 for the CRS-7 mission. This caused a rapid unscheduled disassembly and complete loss of the rocket and its payload. The next failure was the infamous Amos 6 anomaly on September 1st, 2016. Again, an overpressurization due to a failed helium tank in the upper stage caused a complete and total loss of the vehicle as it was being fueled up on the launch pad for a static fire test. Then we have the Crew Dragon anomaly on April 20th, 2019. This is when SpaceX was testing the launch abort systems on the ground and had a frozen chunk of nitrogen tetroxide shoot through the titanium valve, causing a rupture in the system and total loss of the vehicle. And most recently, and perhaps most alarmingly, we actually saw the failure of a Starship Mark 1 prototype on November 20th, 2019, when we watched it blow its top off from an overpressurization during a pressure test. But now this I'll actually give a bit of a pass to. This vehicle and that test was nowhere near future operating conditions. SpaceX was pushing this prototype much further than normal operating ranges, and these were those shoddy welds of the very initial rough prototype, and they don't really represent the future, the more refined vehicle like it will be. But it sure does get a bit spooky when you think that if that was a fully fueled Starship, and there were people on board, that there would have been no aborting from it. So I guess this leads us to the question of what options does Starship have to actually abort? We've already gone over what design considerations make it avoid the same design flaws as the Space Shuttle, but it still is lacking an actual abort system. So can it abort at all? Well, let's first make sure we're clear on the types of abort options. I mean, there's a big difference between a pad abort, an in-flight abort, abort to orbit, and just kind of aborting a mission in general. A pad abort is the option to pull the spacecraft free from the rocket while still on the pad. This is actually a pretty dangerous time while the vehicle is fully fueled, full of highly pressurized explosive material. So can Starship do a pad abort? Yes-ish and no. If the problem is the Starship upper stage itself, like a tank rupture or something, the simple answer is no. But what if the problem is with the booster? If the booster suddenly ruptures, the upper stage of the Starship could perform an emergency quick start of the Raptor engines, which could help prevent the Starship from, just falling down onto a pile of what was once a super heavy booster and is now just a flaming, hellish landscape. If all engines are fired, including its vacuum optimized engines, Starship would have just barely enough thrust to slowly get away from the pad and divert to a safe landing area. That is, assuming a failed super heavy booster didn't damage the Starship bad enough to make it unflyable. Now don't forget, you're not trying to outrun the pressure wave because, spoiler alert, unless you can go 0 to the speed of sound literally instantly, you can't outrun it. So if you're inside of a pressure vessel, you should at least survive the initial blast. You also might ask, how could they fire vacuum optimized engines at sea level? I mean, that was a big part of the Aerospike videos, that you can't really do that. Well, according to Elon, they could have a dual bell design and fix the nozzle to the whole wall, which can help stabilize it. And in general, yes, you can actually fire a standard vacuum nozzle at sea level in an emergency, but it's very likely to fail. But why not try it if the other option is complete failure anyway? So the pad abort, kinda, maybe a little. Well, it's at least better than the Space Shuttle's full lack of abort options while sitting on the pad. The same goes for an in-flight abort. And now an in-flight abort is just what it sounds like, aborting while the rocket is flying. Again, assuming the upper stage isn't the culprit of the problem, the Starship could theoretically pull away and perform whatever maneuver necessary to re-enter and land somewhere else, or worst case scenario, do a soft splashdown emergency landing. Again, it should have more options and opportunities than the Space Shuttle did. Once Starship has detached from Super Heavy, there really aren't any abort options other than just aborting to a safe re-entry profile and then re-entering if it can't achieve orbit. But luckily, with the control surfaces on Starship, they could greatly alter their aerodynamic profile and the dynamics for a handful of safe re-entry options. This is helpful compared to, say, a capsule, which can't change its shape and actually has areas in a launch profile that engineers need to avoid. For instance, If a standard single-engine RL-10 Centaur upper stage was used on Boeing's Starliner, there'd be large portions of the profile where an abort would be deadly due to the extreme re-entry forces. Boeing and ULA therefore had to opt with a 2-engine variant of the Centaur upper stage that could fly a safer profile, which allows for a safe abort window throughout the entire ascent. And of course, on re-entry, there really isn't ever an abort option. I mean, re-entry just needs to work. Even if there was a mechanical abort option during re-entry, it likely wouldn't be very helpful. Now, of course, a passively stable capsule with a simple ablative heat shield has very little that can go wrong. But again, redundant hydraulics for control surfaces and a structure that can handle really high temperatures in general should offer a decent buffer in re-entry for Starship. Okay, we're finally getting to the true meat of the question. Is it actually better to have an abort system on a rocket? Period. To do that, let's quickly go over all the aborts and all the accidents of human spaceflight and determine whether or not an abort system could have helped. Looking at the history of orbital spaceflight, there's only been 18 deaths actually occurring during orbital spaceflight activities. The first death being a parachute failure on the very first Soyuz mission in 1967, which killed cosmonaut Vladimir Komarov. An abort system would not have helped. The next tragedy was Soyuz 11 in 1971, which decompression of the spacecraft actually led to the death of 3 cosmonauts. To this day, this is the only incident in which humans died in space above the Kármán line. Again, an abort system would not have helped. Next, we have the Space Shuttle Challenger disaster in 1986, which we've already talked about. A mechanical abort system would have likely saved the crew of 7. Lastly, we have the Space Shuttle Columbia disaster in 2003, which again tragically killed the crew of 7. An abort system would have likely not helped, but there is a chance that if it had an escape pod and its own little heat shield and the like, that it may have helped, but it's unlikely aborting during re-entry would be a very good option. Now let's look at the number of times a crewed orbital launch escape system has ever been used. The number is very small. Today, an abort system actually armed for flight has only been triggered 3 times. The first time an abort system was used was actually on an uncrewed test flight of Soyuz for the Soyuz 7K OK number 1 mission in 1966. The launch was reset when a strapped-on booster failed to ignite. The ground crew went out to inspect the rocket when suddenly, 27 minutes after the scrub, the launch tower activated because its gyroscope noticed it was 8 degrees off axis from where it thought it should be due to the Earth's rotation. The firing of the abort system ended up lighting the 3rd stage on fire, and then the rest of the rocket blew up on the pad, actually killing 1 ground crew personnel. In this case, an abort system caused a failure and a death. The next time an abort system was fired was the only time there's ever been a pad abort with a crew on board. On September 26, 1983, when the crew of Soyuz T-10-1 had to abort from their Soyuz rocket that had caught on fire while still on the launch pad. After safely aborting and landing 4 kilometers downrange, the crew was bruised up and shaken when they were met by the recovery crew, but they were given cigarettes and shots of vodka to relax. So in this case, obviously the launch abort system saved lives. Lastly, the abort system was triggered on another Soyuz mission, MS-10, in 2018 when there was a problem at booster separation that caused a booster to rupture the core stage. This triggered the abort system. Now, not the full tower, which had just been jettisoned a few seconds prior, but a smaller abort system integrated onto the fairing that covers the crew module. In this case, the abort system saved lives, but perhaps simply shutting down the engines and detaching from the booster would have been sufficient without a mechanical escape system active. There are really only about 2 other flights which were aborted. The first was Soyuz 7K T-39 in 1975, which aborted after the escape tower and fairing were jettisoned. An abort system obviously wouldn't have helped as it had already been ditched. Then there's the only space shuttle to abort, STS-51F in 1985. It performed an abort to orbit maneuver when one of the RS-25 main engines shut down. Again, an abort system wouldn't have helped as it was unnecessary. So in the grand scheme of things, to date, a mechanical abort system has only saved lives twice. It may have prevented 1 tragedy, and in 1 case, it actually created a tragedy. So out of the 320 orbital human spaceflights to date, only 3 missions in total necessitated the use of an abort system, or less than 1% of crewed launches. There were another 3 launches where an abort system wouldn't have helped at all, and 2 that aborted without any kind of escape system. And if we look at the last 30 years of human spaceflight, from the 90s on, only 1 launch out of 180-ish launches required a launch abort system actually be used. So only about 0.5% of flights would see any benefit from a launch escape system at all. Now, before we answer the question, are abort systems necessary, let's just take a look at one more thing. How can we improve the safety of rockets overall so we don't need an abort system, period? I think the answer to this question is we need to fly more, a lot more. And we need to reuse systems over and over and over so we can see where things are the weakest and where we can make the greatest improvements in safety. Let's look at airliner safety. This is a chart showing how many kilometers of commercial airline travel happen per accident over time. Now, unfortunately, this data only goes back to 1929 and doesn't even show the very early Wild Wild West days of air travel. But in less than a century, the industry's safety record improved by 3 orders of magnitude. Now, I really wish we had data on the first 3 decades of human airflight, but unfortunately the data is not available. But I wouldn't be too surprised if it didn't look too far off from this chart. Now, this is actually the orbital launch success rate per year. Notice how quickly humans got into the upper 90 percentile, but then it stalled. Let's compare that to the airline industry during the same time frame. Yeah, humans had pretty much nailed down how you fly by then. So it isn't until you even zoom into the tens of thousands that you can actually even begin to decipher an improvement on flight success rate, because we're well into chasing the 9s in reliability at this point. And I think there's a few reasons for this. First off, in total, there hasn't ever even been 6,000 orbital launches ever. So compare that to the almost 40 million commercial air departures in 2018 alone. And you realize just how rare spaceflight is still. I'll bet the first 6,000 flight attempts of airplanes had a pretty similarly awful flight record as well. I mean, 6,000 flights was probably just achieved in a much quicker time frame and with a significantly lower barrier of entry than building a rocket. Now, we probably really shouldn't be comparing rockets to airplanes, because getting a rocket to space and bringing it back safely is really hard, like orders of magnitude harder than flying an airplane to begin with. I mean, you can make airplanes out of paper, or if you're Peter Sripple, you can make airplanes out of pretty much anything. But it is kind of fun to see how quickly we can actually really improve reliability. It just takes more and more time. But it is kind of fun to compare how quickly things can become reliable once you do them often enough. The answer to what can we do to make rockets more reliable is simple. Fly them more often and fly reusable rockets over and over instead of throwing them away. Only then will we begin to get anywhere near airliner-like reliability. Okay, so it's time we finally wrap this all up. Launch abort systems. Are they necessary? Do they actually make astronauts safer? Do we need them going forward? If so, will we always need them in the future? So remember when we looked at how many times a launch abort system would have saved the lives of crew, and it's a surprisingly small number? Well, I still think it's a good idea for this generation of rockets. I think NASA, SpaceX, and Boeing are right to assume that the Falcon 9 and Atlas V, as reliable of rockets as they are, still lack significant flight data to really be considered safe enough without a launch abort system. But don't forget, launch abort systems still bring their own complications and problems with them. Remember how SpaceX's Crew Dragon capsule blew up when testing the abort system? And actually, Boeing had problems with their launch abort system catching fire on the pad too. Because really, you're basically taking more parts in a small rocket and attaching all these extra systems that can also fail, and you're putting them directly on your crew module anyway. I mean, of course, sure, a lot of work goes into making them safe, but you're solving the problem of rockets by sticking more rockets on them. That'd be like putting a Cessna prop plane inside of a 747. Just in case the 747 fails, you can fly away in your Cessna. I mean, you're probably better off just making sure your maintenance is up to speed rather than going and buying a Cessna. And it's kind of like how people ask me all the time if the Super Draco abort motors could be used as a backup to parachutes if the parachutes fail. And the answer is Well, technically, yes. Of course they could. But by the time you certify that procedure, those systems, and you make them safe and reliable, you probably would have just been better off making sure your parachutes don't fail in the first place, make them more reliable. In the same way, would you rather engineer an abort system, put together all these procedures and envelopes and subsystems, or focus on making the entire vehicle that much safer? At some point, you can actually arguably achieve a more reliable system overall if it has fewer parts. I think Elon Musk actually has a pretty good point when he said this in the 2019 Starship update.
The best part is no part. The best process is no process. It weighs nothing, costs nothing, can't go wrong. So, as obvious as that sounds, the best part is no part. Like the thing I'm most impressed with when I have the design meetings at SpaceX is, what did you undesign? Undesigning is the best thing. Just delete it. That's the best thing. Yeah.
So I guess the question should be, would I ride on Starship without an abort system? For now, the answer is no. I think we should see at least a few dozen flights without crew first. We should find the limits and the boundaries, maybe have some failures or two, and only once we've seen Starship fly 10 plus times reliably without any failures would I consider getting on one. But I'm also kind of a chicken, and I don't think I'm cut out for anything less. I do think it could be possible we see humans, who are willing to risk it, on Starship early on in the program. And if it's NASA astronauts on board, I wouldn't be surprised if they would require an abort system, especially since SpaceX will likely load and go their fuel, just like they do the Falcon 9, meaning the crew will need to be on board as fuel flows. In general, it's more dangerous to be filling and pressurizing a vehicle than to have it just sitting there stable and fully fueled. So unless SpaceX can change that procedure for Starship, I honestly can't really imagine NASA wanting any of their astronauts on board without an abort system again, anytime soon. At the end of the day, you can't fix the problems you don't know are there. Just like how SpaceX was so surprised to discover problems with cryogenics and composite overwrap pressure vessels, or the failure of a strut, or a titanium valve exploding. I mean, sometimes you just simply don't discover a design flaw until it rears its ugly head. So that's why I think it's vital we see these things fly often, and fly over and over. Only then will I think there's a proven reliability track record that would make it a safe enough option to not have an abort system. So what do you think? Abort systems. Are they good? Are they bad? Would you get on a rocket that doesn't have an abort system? I mean, at the end of the day, that's really what it comes down to. I mean, I can see both sides of this argument. I can see where you might say, obviously it can make things safer because if the rocket fails, you at least have a backup rocket. But at the same time, you're adding more parts. So maybe there's some elegance to the simplicity of a design that doesn't have all these extra parts and just focus on making those more reliable. But I don't know. Let me know your thoughts in the comments below. And also be sure and let me know if you have any other questions about, Starship, abort systems, stainless steel, Raptor engines, space shuttles, anything. Let me know if you have any questions and I'll be sure and try and crank out it on my video list. I have this never-ending video list that I just cannot keep up with, but I'm really excited to keep cranking away at them. So stay tuned. There's a lot of really good content coming. As always, I owe the biggest thanks in the world to my Patreon supporters who literally help me do all of this stuff. They've been a big help on this video, trying to find all these fun facts and find little nuggets of information with me, crunching numbers and confirming my stuff is accurate. So if you want to help do what I do, please consider becoming a Patreon supporter by going to patreon.com/everydayastronaut, where you'll gain access to our exclusive Discord, Patreon, and exclusive live streams. And while you're online, be sure and check out everydayastronaut.com/shop for limited edition merch. Now, do notice the merchandise is getting awesome. We have they're all hand screen printed, hand sewn on patches, custom neck labels, all these really cool things, and these awesome designs are limited run. So if you like something, you better grab it now because there's a good chance it won't be there next time you click on the website. And I guess you can even grab what's apparently one of Elon Musk's favorite shirts, the full flow stage combustion cycle shirt. We also have that as a hoodie version as well, just in time for the cold weather. So get in there while you can and get some awesome merchandise for yourself. That's everydayastronaut.com/shop. Thanks, everybody. That's going to do it for me. I'm Tim Dodd, the Everyday Astronaut, bringing space down to Earth for everyday people.